Okay guys, Lewis structures. This is the thing I did the most of over the last few weeks. They're very important. I looked at some practice exams for Gupta's class. They had them on there. And for Jules, it seems like she's stressing them more, so I think they're definitely going to be on her exam. So let's start out by talking about the different types of geometry. So first off, we have linear, which is just three atoms attached to each other by two bonds. Then we have bent, which looks similar because it's three atoms attached by two bonds, but they're in a bent fashion. All right, we're back. Okay, so we got trig planar comes next, which is three bonds around a central atom attached to three different atoms, and it's flat. Trig pyramidal. Which is also three bonds attached to that central atom. Oh my goodness, everything's opening. Three bonds attached to that central atom, but there's a lone pair here that push those substituents down. So if you look from linear and bent, and also from trig planar to trig pyramidal, the only difference between the two is the presence of lone pairs. What those lone pairs do is they cause those substituents on the sides to be pushed down. All right, so if there's lone pairs present, then it is going to be bent or trig pyramidal. If there's no lone pairs, it's going to be trig planar or linear. And then the last one is tetrahedral, which is just four bonds around a central atom attached to other atoms. So when you look at the prefixes in the last three, okay, try, in these first two, in trig pyramidal and trig planar, they both have three bonds. That try says how many bonds there are. So there's three in trig planar, three in trig pyramidal. Tetrahedral, you look at the tetra, that means four. So there's four bonds on the central atom. So that's an easy way to keep that straight. So now let's jump into drawing the Lewis structures. So my first step is to find out how many electrons are being brought to this molecule. Okay, so we have Be and we have F. So I know that F has 7 valence electrons, and there's two F's attached to this central atom. Therefore, it has a total of 14 being brought by the F's. Now let's look at Be. If we can find it on the periodic table, it's all the way over on the left. It's number 4, and it has 2 valence electrons. So if we come back, Be has 2 valence electrons, and there's only one atom of it. It's a total of 2 electrons. So when you sum it up, you get a total of 16. So now let's determine what the central atom is. So 90% of the time, the central atom is going to be what's listed first. Just something to keep in mind is halogens, which is the group all the way to the right that is not the noble gases. So this is the noble gases, not them. One to the left. So fluorine, chlorine, bromine, iodine, and the other two. Those can only form one bond, therefore they cannot be the central atom. Same with hydrogen. It can only form one bond and cannot be a central atom. So once we jump back in, so fluorine, that's one of those halogens, so it cannot form a double bond, or it cannot form multiple bonds. Be has 2 valence electrons and it can form 2 bonds. So Be, let's go F on this side and F on this side. So the next step is I fill out everybody's octet to 8. So this F has 2 electrons participating with it because the electrons in the bond count for both the F and for the Be. So you need to put 6 more electrons on the F, on either F. And then Be only has 4 interacting with it, so you got to put 4 more till you fill its octet. Now when we sum it up, we're at 20 electrons in this structure, which is not the same as the 16 that we have right above that, right? So what we have to do is there are two things that could happen. First, I would check if we can form multiple bonds. And since these are halogens on either side, that is not possible because halogens cannot form more than one bond. And a double bond is more than one bond. So then the next thing you have to look at is what your central atom is. So Be, I look at the periodic table, it's all the way over here on the left, meaning that it has 2 valence electrons. So it is completely okay only having those 2 bonds, because what actually happens in 3-dimensional space is you have Be with its 2 valence electrons just chilling. You have F's come along with their 7 valence electrons. And then these attach to make a bond, and these attach to make a bond. Now, this is not the most stable form for this molecule, but it's the most stable that we can have with the electrons that we have. Because Be, it's not very reactive because it doesn't have more electrons that can react, but it's not as non-reactive as if it had a full shell. But it is completely content with just sitting like this. Another example of this is boron. Boron has 3 valence electrons, so it's completely content just making 3 bonds and then having this open up here. Okay, so let's move on to the next one. All right, let's try molecular geometry here. So it's 3 atoms attached by 2 bonds, so it's immediately narrowed down to either linear or bent. And when I look at the central atom, there are no lone pairs left on it once we have deduced it to the correct number of electrons. Therefore, it is linear. So, next one, we have N and I. I has 7. There's 3 I's. It's a total of 21. N has 5. There's 1 N, so it's a total of 5. That totals to 26. So let's draw N's the central atom. I. Fill out everyone's octet. And then count out the bond, or the electrons in the bonds and in the lone pairs around it. And we sum up to 26, which already equals the amount that we're supposed to have. So we know that that is the correct Lewis structure. Now, this is a central atom with 3 bonds attached to it, so we already narrowed it down to either trig planar or trig pyramidal. And since there is a lone pair present on that nitrogen atom, it is going to be trig pyramidal. All right, let's move on to the next one. Okay, so this is SF5. So this is kind of like the same concept of the first one and BF3. So what we know about sulfur is that it has... Okay, I'm going to change this one. You won't see SF5. I'm just going to erase it. See, it's gone forever. Okay, let's move on to PBr5. Yes, this works. This is what I was trying to do with the last one. Sorry about that. Okay, so let's do PBr5. So I'm going to go sorry, that's not how you write Br. So then P has 5 valence electrons. There's only 1 in the molecule, so that's a total of 5 electrons. Br has 7 valence electrons. There's 5 of them, so that's going to be 35. So that's a total of 40 electrons. So, when we look at P, it has 5 valence electrons, right? Just like nitrogen. So, it can either form 5 bonds or 3 bonds. The reasoning for this is because electrons want to be in pairs, whether it be in a lone pair, like they are up here, or... How did that not erase the circle? There we go. Or in a bond, like they are all around the P. So, see how like they're kind of paired up? That's more stable. So P either wants to hold 3 bonds, or it can be attacked on this electron, and then that would leave a lone electron, which is incredibly unstable and would cause another bond to form with something else. So that is the case here, and since we have Br5, then we know that P is going to have 5 bonds coming off of it. Br, 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 Br. Okay, so let's go ahead and fill in the electrons. P already has more than its octet, so we're not going to put any more lone pairs on him. And then when we count that up, we get to our 40, so we know that it's correct. And this is a molecular geometry that you do not know, or do not have to know. It's called, I believe it's trig bipyramidal. So basically, this one, and this one are flat, and then this one comes straight out the top, and this one comes straight out the bottom. But I don't think you have to know those. Now, CCl4, different story. This is one that you'll have to know. So carbon has 4 valence electrons, Cl has 7. We have 4 Cls and just 1 carbon. Total of 4 electrons coming from carbon, 28 coming from chlorine. No. Yeah. Okay, cool. Math is hard. So that's a total of 32. So we got C in the middle, and then Cl all around it. We fill in everyone's octet to the full 8 electrons. And once we count up all the electrons present, we get to our total of 32. So we know that this is the correct Lewis structure. And then we see 4 bonds around a central atom, so that is tetrahedral. All right, next video.